welcome to BCP Med. In this video, I want to break down the impact of molar mass and electron cloud polarizability on the strength of London dispersion forces. We're going to be going in depth into things like electron cloud size, quantifying polarizability with alpha values, and some nuances with pi bonded systems. Let's go ahead and get started. To understand the impact of molar mass on LDFs, we first have to understand what impacts the magnitude of a dipole moment to begin with. We can see from our formula here that the dipole moment mu is equal to the charge being separated times the distance. Now, an increase in molar mass leads to a roughly proportional increase in the number of electrons because you get one electron per new proton. It's not quite proportional because neutrons also add mass without more electrons, but you get the gist. Simply having more electrons in the cloud allows for a larger dipole moment because a larger partial charge Q can accumulate on either side of the molecule. For example, if we look at a smaller molecule shown here on the bottom left, its separation of charge is rather small. Whereas if we look at this one here on the right, when it skews its electron cloud, we see a much larger buildup of partial charges, and therefore a stronger dipole moment. So, to sum it up, the larger electron cloud allows for a stronger dipole moment to be created by probabilistic skewing because it allows a larger charge to develop, which ultimately leads to stronger electric interactions between molecules, that is, stronger London dispersion forces. To view this in a more empirical setting, we can consider the following series of hydrocarbons, where the chain increases by one carbon in each successive molecule from left to right. If you look at the boiling points below, there's a nice and steady increase in the boiling point for each species. In fact, it becomes almost linear past the first species, increasing by about 40 degrees Celsius per new carbon added. The trend is pretty obvious, right? As electron cloud size increases from left to right with the addition of one more carbon, the boiling point increases by a similar amount. Therefore, the London dispersion forces must be increasing, since there's no other intermolecular forces at play, and these are all nonpolar molecules. Now, in addition to just the raw size of the electron cloud, we also need to think about how polarizable it is. Polarizability, which is often represented by the symbol alpha, is a measure of how easy it is to distort the shape of the electron cloud. In other words, how easy is it to make the electron cloud go from nice and symmetrical to asymmetrical with partially charged ends? Because it measures the ease of creating transient and induced dipoles, polarizability is a good measure of how strong dispersion forces are. The factors that influence polarizability include the number of electrons in the electron cloud, right? The more repulsions there are, the more inclined the electron cloud is to spread around. The size of the electron cloud. The bigger the electron cloud is, the easier it is for electrons to go ahead and move around the nucleus and spread out. And the electronegativity of the electron cloud as well. The electronegativity dictates how tightly the electrons are held. And so the more electronegative the nucleus is, the less polarizable the cloud is going to be, right? The less easily the electrons are able to just slosh freely around and stretch further apart from the nucleus. So let's go ahead and look at some examples. On the left, we're going to have fluorine, and on the right, we're going to have bromine. These are both halogens. They're both single atoms. We're not going to worry about molecules yet. On the left, fluorine is going to have an electronegativity value of about 4. This is the highest on the periodic table. And it's also going to have a radius of 60 picometers, which is very small even for atoms. And because of that, it's going to have a polarizability value of about 0.557 alpha, which, if you've never seen polarizability values before, that really means nothing to you, but I'm going to go ahead and tell you that's very low. And that makes sense. Because fluorine is so electronegative, and because it's so small, those electrons are going to be held really tightly and they're confined to a small space. They're not going to be able to move around very much. On the other hand, bromine is going to have an electronegativity value of about 3 and a radius of about 180 picometers, which is 3 times that of fluorine. So because it's much larger, it's going to have a polarizability value about 6 times higher at around 3. And from this, we would expect bromine to have much stronger London dispersion forces than fluorine. Now, with individual atoms, we can't really gauge the intermolecular forces, but we can with molecules, and that's what we're going to do next. So, indeed, what we're going to do now is go ahead and consider the boiling points of the diatomic halogen species, fluorine, chlorine, bromine, and iodine. Because these are all homonuclear, that's all just one kind of element, They're all completely non-polar, so LDFs are the only thing we need to think about here. Empirically, we're going to see that the boiling point increases from the left-hand side to the right-hand side towards the heavier halogens, with iodine boiling at almost 400 degrees Celsius higher than fluorine. And we see that these molecules obey the pattern that we've laid out before very nicely. Molar mass and polarizability increase to the right-hand side of the table with boiling point, just like we would expect. Iodine is a much larger atom than fluorine, and so it is going to be much more polarizable and also much heavier, and so it is going to have a much higher boiling point with stronger LDFs. On the other hand, fluorine is the most electronegative of these species, so it's going to be the most tightly held electron cloud, and as a result, the least polarizable, and therefore the lowest boiling point. So clearly the relationships we've laid out make sense. The trends are still obeyed for the halogens here. So this relationship between electron cloud polarizability and dispersion force strength is very important, and it leads to some really neat effects in double bonded systems. Conjugation, which is a series of alternating double bonds, has a very unique effect on polarizability and ultimately boiling point. Conjugated bonds are said to be delocalized, which means that they act like one large bonding system, one giant electron cloud, rather than individual bonds, which means the electron density can move somewhat freely throughout the entire length of the conjugation, which of course increases polarizability because it's acting like a larger cloud and polarizability increases with size. So if we go ahead and look at this molecule on the left, this is what is known as an unconjugated pi system. Right? This double bond, there's only one of them, and so it is localized to where it is drawn on the structure. It is just that double bond and that's it. So this will have a short travel path for the electron cloud. Right? It cannot move very much. It is localized to move just where that blue arrow is. And so it's going to have a relatively low polarizability. On the other hand, if we go ahead and look at this pi system, this is going to be conjugated. We see these alternating double single bonds. And so this entire molecule, like we said, is going to behave like a single larger electron cloud, right? We're going to have this very large travel path indicated by this blue arrow above the molecule, right? So this electron cloud the electrons can move freely, relatively freely, back and forth across the entire length of the molecule, making it very polarizable. And indeed, we can go ahead and look at some boiling point data to corroborate what we're expecting, based on the polarizability argument. So if we look at these three molecules, which are going to increase in the length of their conjugation system from 1 to 2 to 3 double bonds from left to right, we would expect the one on the right to be the most polarizable and the one on the left to be the least polarizable, based on the length of their conjugation system. This is exactly corroborated by the boiling point data. The one on the right has the highest boiling point. It has the strongest London dispersion forces, whereas the one on the left, being the least polarizable, has the weakest. And you might be wondering, well, how do we know it's the London dispersion forces and not something else? Well, none of these molecules are polar. All of these are going to have the exact same dipole moment of 0. And moreover, the one on the right actually has a lower molar mass than the ones on the left. Odd, right? Well, it turns out that every time you add a double bond, you have to remove some hydrogens. So every time we add that double bond, we're losing 2 hydrogens. So the one on the right is actually smaller in terms of the electron cloud, but because it's so much more polarizable, because the electrons can move so much further, it's going to have a much stronger dispersion force and a higher boiling point. Finally, let's take a quick look at some more macro examples of LDFs and their relation to molar mass. While small molecules tend to exhibit very weak dispersion forces, larger molecules have incredibly powerful ones, owing to their chains, which can be thousands of atoms long. These dispersion forces can help anchor proteins like this globular protein shown here in membranes. They actually determine the structure of globular or spherical proteins in aqueous environments where they make the molecule stick to itself rather than dissolving in water, which hydrogen bonds. So the dispersion forces like to stick to their own. They don't like to mix with other intermolecular forces. They can also determine the enzyme active sites of proteins. They actually are so powerful that they can form these semi-rigid regions of proteins which can act as mini chemical reactors to catalyze other reactions. Another thing that we should look at is phospholipids, right? The tails of phospholipids, which are the molecules that make up your cell membranes, are long nonpolar chains, and as a result, they're all glued together by London dispersion forces, not dipole-dipole forces, not hydrogen bonding, just LDFs. So in a very real sense, LDFs are the reason your body is able to hold itself together. It's how your cell membranes hold themselves together, and it's also how the cell membrane is selectively permeable, how it regulates what goes in and out of the cell. So with that, we've reached the end of the content for this video. Thank you guys so much for watching, and if you enjoyed what you saw, please like and subscribe to the channel. Also, make sure to check out our other videos on the chemistry playlist to learn more. And if you're looking to branch out and learn some different things, check out our other science playlists. Thank you for watching and see you next time.